And first of all, I'd like to thank Professor Sun-Sik Kwon for this kind invitation and for giving me this opportunity to give a talk. And this is the second time to visit Korea. And in the first time, I visited Suwon more than 10 years ago. And this is the second time. And I'm very happy to be here. And I'm mainly working on the mathematical theory for water waves, but for more than 20 years, so a long time. But recently, in the last several years, 4 years, 5 years, I was interested in analyzing this Isobe-Kakinuma model. This is a model for water waves, and this model was proposed and derived by Professor Isobe and Kakinuma. They are Japanese researchers, but they are not mathematicians nor physicists, but they are working on the coastal engineering. And they derived their model by using variational structure of the water waves. And actually, Professor Kakinuma, he is one of my friends, and someday he asked to me, how do I think their model from a mathematical point of view, from the point of view mathematician, but at the time I couldn't answer to his question. So in order to answer his question, I started this research. This is a motivation of mine to this research. And today I'd like to introduce some basic structure of this model. In some sense, this is some strange model, but finally we found that this is a really higher order shallow water approximation. Okay, let me formulate the water wave problem. And in the previous talk, Professor Ha explains what is a water wave problem. And so we consider the motion of the water in n+1 dimensional space, and we assume the shape of the water region is something like this. Here, this is a water surface. And this blue region represents the water, and this is the bottom of the water. And we take the gravity into account as an external force. This is an important external force. Here, G is a gravitational constant. And moreover, we assume this water surface and the bottom are represented as graphs like this. Here, H, which is a positive constant, represents the mean depth of the water. And eta is the surface elevation of the water surface. And here B represents the bottom topography. And in this problem, B is a given function, while eta is a main unknown function. And as usual in the analysis of water wave, we assume the water is incompressible and ideal fluid, and the flow is irrotational. Then, the fluid motion is described by the following system of equations. Here, capital Phi is a velocity potential. Namely, the gradient of Phi is a velocity field of the water. And the first, this Laplace equation, this is nothing but a Laplace equation is a continuity equation which represents the divergence-free condition in the water region. So this is a continuity equation. So this one is irrotational? Irrotational, yes. So therefore, we can introduce the single-valued velocity potential, capital Phi. And the second equation is Bernoulli's law restricted on the water surface. And the second one is a kinematic boundary condition on the water surface. So these two equations are the boundary condition on the water surface, while this is a Neumann boundary condition, homogeneous Neumann boundary condition on the bottom. This is also a kinetic boundary condition, which means that on the bottom there is no inflow, outflow. Here, in part follows, we use standard notation of lambda, and the Laplacian is a Nabla Laplacian with respect to the horizontal spatial variables, and the Nabla Laplacian with suffix capital X as a Nabla Laplacian with respect to the whole spatial variables. So these are the basic equations for the water waves, and this is the starting point of our argument. But however, there is another equivalent formulation of the water wave problem. So now we put small phi as a trace of the velocity potential capital Phi on the water surface. Then we see that the eta is surface elevation, and this trace phi satisfies the following closed equation in terms of eta and phi. So nowadays, these equations are equivalent to the original one. And nowadays, this formulation of the water wave problem is called the Zaharoff formulation or the Zaharoff-Craig-Slam formulation. In fact, in 1967 or 8, Zaharoff shows that eta and phi is a canonical variable. Namely, the water wave problem has a Hamiltonian structure, and the Hamiltonian is total energy, and the canonical variable is eta and phi. And later, by using here we have some notation capital lambda, which is a Dirichlet-to-Neumann map for the Laplace equation. By using explicitly this Dirichlet-to-Neumann map, the Walter Craig and Slam write down explicitly these equations. But this equation is equivalent to the Zaharoff's canonical form. And this Dirichlet-to-Neumann map can be defined explicitly as follows. Under appropriate assumption for the water surface and the bottom, for example, the Lipschitz continuity of these two surfaces, for any function phi on the water surface in some class, for example, H1, this boundary value problem for the Laplace equation with this Dirichlet boundary condition on the water surface and this Neumann boundary condition on the bottom has a unique solution, capital Phi. And by using this solution, capital Phi, we define the map lambda by this formula. So this means this lambda maps the Dirichlet data on the water surface to the Neumann data on the water surface. So therefore, we call this map is a Dirichlet-Neumann map. Since, of course, this is a simple linear equations, so this map is linear operator. However, this operator depends on the unknown water surface, unknown water region, omega t, namely, which also depend on the unknown function eta. And this dependence is strongly nonlinear. And in the case where the surface, water surface and the bottom are flat, then Dirichlet-Neumann map can be written explicitly in terms of the Fourier multipliers like this. So this is the operator of order 1 because it maps the Dirichlet data to the Neumann data. So it is natural. Anyway, we can formulate the water wave problem to this form. So this is the equation, in some sense, integral differential equations in the whole Euclidean space Rn. So this is no more free boundary problem. This is the equations for the Rn. Next, let me explain the variational structure of the water waves. In 1967, Luke showed that the water wave problem has a variational structure, and his Lagrangian, or more precisely, his Lagrangian density is given by this in terms of the surface elevation eta and velocity potential capital phi. And the action is nothing but a space-time integral like this. And he shows that the corresponding Euler-Lagrange equation is exactly the same as the basic equation for water waves. In fact, let's calculate the first variation of this action function. And after that, by taking the first variation and after the integration by parts, we have the following formula for the first variation of this action function. So first one is the volume integral in the water region. And these two integrals, second and third integrals, are the surface integrals on the water surface. And the last integral is the surface integral on the bottom. So now we take the first variation of the velocity potential, capital phi. Then we can recover the Laplace equation. We can recover the continuity equation in the water region. And if we take the first variation of the surface elevation, then we can recover this should be equal to 0, which is Bernoulli's law restricted on the water surface. And if we take the first variation of the trace of the velocity potential, then we can recover the kinematic boundary condition on the water surface. And finally, if we take the first variation of the trace of the velocity potential on the bottom, then we can recover the Neumann boundary condition on the bottom. So therefore, the corresponding Euler-Lagrange equation is exactly the same as the basic equation for the water wave problem. And Professor Isobe and Professor Kakinuma used this variational structure to derive their model. In 1994, Professor Isobe approximated the velocity potential in this Luke's Lagrangian by this formula, where Ci appropriate function system with respect to the vertical spatial variable, and which may depend on the bottom topography, whereas phi is unknown, just unknown coefficient. In this approximation, we should specify this function system psi, whereas phi is unknown. So now, plugging this approximation into this Luke's Lagrangian, then we can obtain the approximate Lagrangian for these unknowns: surface elevation eta, phi naught. Usually, this is a trace of the velocity potential on the bottom, and the other one is nothing but just coefficient, a known coefficient. And their model equations as a corresponding Euler-Lagrangian for the approximate Lagrangian. And different choice of this function system gives a different model for the Isobe-Kakinuma model. So what is the best choice of this base function? The key is given by the following formula. In the case of the flat bottom, in 1872, Buzinesque gave this formula. So this is nothing but the Taylor approximation of the velocity potential capital phi with respect to the vertical spatial variable around the bottom. where phi naught is a trace of the velocity potential on the bottom. So, in the case of the flat bottom, maybe the good choice of the base function is a polynomial of these polynomials of even degrees. However, for the general case, for the general bottom topography V, we do not have such a simple formula, but again, we can also expand. We have the Taylor expansion of the velocity potential capital phi with respect to the vertical spatial variable around the bottom, like this. But in this case, we have all order of this polynomial. So in that case, we should use all of them. And I'd like to treat both cases at the same time. So we choose the function system as follows. Let phi 0 phi I blah 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 phi capital N be integers satisfying this outer ring. And now we approximate the velocity potential capital phi by this function, which is a polynomial with respect to the vertical spatial variable. And practically, we choose pi equal to 2i in the case of the flat bottom, and pi equal to I in the general case. Now, we plug this approximation into Luke's Lagrangian L. Then we obtain the approximate Lagrangian of these unknowns, capital N plus 2 unknowns. And actually, it is not difficult to integrate this Luke's Lagrangian. Then we have the following expression of the approximate Lagrangian. It's a little bit complicated, but for the moment, the explicit expression is not so important. Here, capital H, frequently I use this notation, and this is local dips at the point x at time t. So this is a dips. And so we can easily obtain the corresponding action function, and it is not so difficult to the corresponding Euler-Lagrange equation. And in our choice of our base function, the Isobe-Kakinuma model has the following form. A little bit complicated. So it is not so easy to answer his question. So how do you think? Okay, I should explain a little bit about these equations. But yeah, you may think that these equations are a little bit complicated. Maybe complicated than the original model, but in the point of view of the numerical calculation, this is much simpler than the original model. And if we take the first variation of the approximate Lagrangian with respect to the phi I, we obtain the first equation. Here we have time derivative only here. So this is an evolution equation for eta. Eta is the surface elevation. And this equation contains up to the second order derivative of phi j and the first order derivative of eta. However, the index I move from 0 to capital N. It means that we have capital N plus 1 evolution equation for just one unknown eta, which means that this is overdetermined equations. And if we take the first variation with respect to the surface elevation eta of the approximate Lagrangian, then we obtain the second equation. We have only here the time derivative. So therefore, this equation is an evolution equation for capital N plus 1 unknown phi I, and which include up to the first order derivative of phi j, and there is no derivative of eta. So this means that this is underdetermined evolution equation for phi I. So Isobe-Kakinuma model is in some sense overdetermined, the underdetermined coupled system. But anyway, the total number of unknowns is equal to the total number of the equations. And now we consider the initial value problem to this Isobe-Kakinuma model under this initial condition as usual. And so first, we'd like to know this initial value problem is ill-posed or well-posed or ill-posed. Before giving our result concerning the well-posedness of this initial value problem, let's consider the linearized problem. So when we faced on such a complicated equations, the first step is to calculate the dispersion relations. So now let's calculate the dispersion relation of this Isobe-Kakinuma model. So now let's consider the case of the flat bottom, and we linearize the Isobe-Kakinuma model around the trivial flow, and we rescale. This is nothing but the rescale with some positive constant of phi j. And then the linearized equation have this form. Here, the time derivative, gh, the positive constant. A is matrix differential operator, which has this form. Here, the second order differential operator, and the coefficient matrix A0 and A1 is a constant coefficient matrix, which is given by this. So now, the linear dispersion relation is given by this determinant, where z is a wave vector and omega is the angular frequency. And so this diagonal part coming from this, and here this matrix is a symbol of this differential operator. And off diagonal part here coming from this. So the dispersion relation is nothing but, so if we we want to find the plane waves, non-trivial plane wave solution of this form. So if omega and z is free, then this is not, of course, this is not a solution. In order that this is the solution of the linearized system, omega and z should satisfy some relation, which is so-called the linear dispersion relation. And in this case, the linear dispersion relation is given by this. And we can expand this determinant as follows. Like this. Here we have here omega only here. So this is very, very simple quadratic equation for omega. And here we have determinant, and a tilde is defined by this. Yeah, defined by this, which is calculated from this original matrix A. So now we need to know the behavior of these two determinants. And concerning to these determinants, we have the following propositions. So for any wave vector z, which is not equal to 0, then this symmetric matrix A is positive. So this determinant is always positive. But if z equal to 0, then this matrix has 0 eigenvalue, so this becomes 0. But anyway, not negative. And here, this is no more symmetric but the determinant is always positive definite. So this is positive. So therefore, we can solve this quadratic equation for omega in terms of omega easily. And the solution is always real. So therefore, we can define the phase speed for the wave vector Guzzi, which is given by omega divided by the wave number. So this is the phase speed. And we will denote, which will be denoted by C, IK. IK means Isobe-Kakinuma. Now actually, this phase speed depends on the wave number Guzzi. If Guzzi changes, then this phase speed also change. It means that the Isobe-Kakinuma model has some dispersion property. So therefore, the Isobe-Kakinuma model falls into the nonlinear dispersive equations. Okay, now we know that that model is the nonlinear dispersive equation. But on the other hand, Professor showed that present that the phase speed for the full water wave problem is given by this. She used the notation, so absolute value of Guzzi is, she used K. So which will be denoted by C omega omega. Omega omega means water waves. So let's compare these two phase speeds. And we have the following theorem. Here Nemoto was my former student. And the theorem is as follows. We choose Pi equal to 2I. So in the physical point of view, in the case of the flat bottom, this is most natural choice. Namely, if we approximate the velocity potential by this, then the square of the phase speed of the Isobe-Kakinuma model is the 2n pas de approximant of the square of the phase speed of the full water wave problem. Pas de approximant is the approximation by the rational function, and the denominator is the polynomial of order of degree to n, and the numerator is also the polynomial of degree to n. Among such rational functions, pas de approximant gives the best approximation. And more precisely, we have following estimate. These differences is estimated by this one. So roughly speaking, this quantity represents the ratio of the mean dips to the wavelengths. And in the shallow water regime, if we consider the shallow water, this one is small. But we have this very high order. In the case of the nonlinear the shallow water equation, this order is 2. And we have so-called Green-Nagel equation, which is known as a higher order shallow water approximation. In that case, this order is 4. But in our case, if we take n, if we take capital N equal to 0, then the Isobe-Kakinuma model is exactly the same as the nonlinear shallow water equation. So it's consistent. But if we take n, if we put one more unknown function, then the error becomes the 6. So we skip the order of the Green-Nagel equation. If we take capital N equal to 2, it's 10. It's enough. It's too much good. So therefore, it means that at least in the linear level, we see that the Isobe-Kakinuma model is a higher order shallow water approximation.
Excuse me, is it the flat bottom case?
Yes. flat bottom case. But in the general case, almost the end of my talk, I will talk on that part. And finally, I will talk that part later. And in the case where if we choose Pi is equal to I, actually in the case where bottom is non-flat, this choice is important. And in that case, we do not have such a previous beautiful result, but we still have this result. This part is still high. So roughly speaking, this theorem says that this order is determined the term of even order only. If we add the term of odd degree, this order doesn't change. So the term of odd degree do not makes worse or the good, not good, not bad. Just this order determined only on the term of even degree. Okay, now go back to the nonlinear problem. This is.
So, in the statement of the theorem, is there any reason why you compare the square of something? Because if we directly compare, we do not have such a beautiful result. But this is a maybe technical reason. I cannot say. For example, in the KdV case, this is the Taylor approximation up to the first order. And the other example is BBM equation, Benjamin Boda-Mahoney equation. BBM equation is 0 to Paddy approximant. We can compare directly the phase speed. And the phase speed of the Benjamin Boda-Mahoney BBM equation is 0 to Paddy 1 to Paddy, 0 to, I guess 0 to Paddy approximant of the phase speed of the full water wave problem. In that case, we can compare directly the phase speed. But for example, in the Green-Nagdi equation, I did not write down that equation. In that case, it's a square. In that case, we have some similar result. So in the case of the Green-Nagdi equation, so this is 0 to Paddy approximant. If we compare the square, so this means that essentially the ether satisfy the equation of the second order with respect to time in these cases. But for example, the KdV, the BBM is a first order evolution equation in time. So this is some difference. Okay. So therefore, it is not trivial that the difference of the solution obeys the same order. It is not trivial. We need to show because we just compare the square. But we can do it. Okay, now so this is a nonlinear problem for the Isobe-Kakinuma model. So now it is well known that the full water wave problem has three conserved quantities: mass, momentum, and the energy. So the mass is given by this, and the momentum in the horizontal direction. And if we use
Gauss's divergence theorem, Green's formula, we can write this one to the surface integral. And this is horizontal momentum is a conservative quantity in the case where the bottom is flat. Otherwise, if bottom is not flat, the momentum does not conserved. And the energy is given by this is kinetic energy. So this is a v square. So this is a kinetic energy. V is a velocity. And here G, so this is potential energy due to the gravity. And if we use the Green's formula again, then we can rewrite this volume integral in terms of the surface integral on the water surface. And this is equal to this one. So these three quantities are conserved. And as for the Isobe-Kakinuma model, the corresponding quantity is also conserved. So mass is conserved. In the case of the flattened bottom, the horizontal momentum, which is defined by this in terms of the variable of Isobe-Kakinuma model, and this is conserved, and the energy is also conserved. Here, capital phi is replaced by our approximate velocity potential. So this has a conserved quantity. It's very important for the numerical calculation. For the numerical calculation, in order to check the accuracy, we need some. We use sometimes such conserved quantities. And until now, I just present some good feature, only good feature of the Isobe-Kakinuma model. But the Isobe-Kakinuma model has serious drawback. So the Isobe-Kakinuma model can be written in the matrix form like this. Here we have some time derivative, and here we do not have time derivative, only on the special derivatives. So, and here, if capital N is strictly positive, greater than 1, then this matrix has always 0 eigenvalue. So this means that the hypersurface T equals 0 is characteristic for the model. It means that if we impose the initial data arbitrarily, sometimes we can, there is no solution. In fact, so this is an overdetermined system. So here we have capital N plus 1 evolution equation just for one scalar unknown function, eta. So from these equations, we can easily eliminate the time derivative of the surface elevation, eta. And we obtain some differential equation which does not contain any time derivative, which is given by this. So here we do not have any time derivative. So therefore, the initial data should satisfy these equations. Otherwise, the solution doesn't exist. So the question is, if initial data satisfy these equations, then can we show the well-posedness of the initial value problem? The answer is yes. But in order to present our result, I'd like to explain the professor has also explained some importance of the sign condition of the pressure. It is known that the well-posedness of the initial value problem for the full water wave problem may be broken unless the following sign condition is satisfied. So she explained the importance of this sign condition. This is almost necessary. This is just as a sufficient condition, but it is almost necessary and sufficient condition. It means that if this quantity becomes negative in some part, then we can show the ill-posedness of the initial value problem. So therefore, this is almost the equivalence. But the difficulty is some degeneracy. In the case equal to the, so in that case it degenerates. So we cannot say that this is necessary condition. This is just the sufficient condition, but almost necessary and sufficient condition for the well-posedness of the initial value problem. So therefore, this is important condition, and we want to translate this condition in terms of our variable. Because we do not use the pressure capital P. How we translate this condition in terms of our variable? To this end, we use Bernoulli's law. Here, this is a Bernoulli's law. So now, if we replace capital Phi and P by our approximate velocity potential Phi approximation and approximate pressure capital P, then we obtain this one. So approximate pressure in some sense should be given by this formula. And we have explicit formulation, explicit expression of this approximate velocity potential. And we can calculate this quantity, which this quantity should be positive, and which is equal to this one in terms of the variable, a non-variable of Isobe-Kakinuma model. So we will denote this one by A. So now we can give our main result, one of our main result in this talk. So if initial data and the bottom topography satisfy the necessary condition for the existence of the solution and satisfy some regularity and the positivity of the dips. So yes, and the sign condition for the initial data, then the initial value problem for the Isobe-Kakinuma model is well posed. So that model is not so bad, at least not so bad. If this is ill posed, it means it is bad, but it is not so bad. Okay, but we need to show that initial data should satisfy the necessary condition. It's a little bit complicated condition. So these equations. For example, in the numerical simulation of tsunami, usually we suppose that the initial water surface is equal to the permanent shift of the seabed due to the earthquake, and the initial velocity is equal to 0, which corresponds to the each phi I is equal to 0. So in that case, this condition is automatically satisfied. But so typical example is okay. But how about the other case? So before I explain that the Zakharov shows that phi eta, the surface elevation, and phi, the trace of the velocity potential on the water surface are the canonical variable. So this is a good variable. So I guess that nobody posed the objection to impose the initial data for these canonical variable. So it is natural to impose the initial data of eta and this phi. Now let's relate this phi with our variable of the Isobe-Kakinuma model. So in order to obtain such a relation, we just replace phi by our approximation. Then we have this relation between the canonical variable and the variable of the Isobe-Kakinuma model. So the following proposition, we have the following proposition. It says that if we give the initial data to the canonical variable, so now if we impose the initial data of this quantity, then this relation and the previous necessary condition determine uniquely the initial data for the Isobe-Kakinuma model. Roughly speaking, this relation together with the previous necessary condition forms some elliptic equation, which is coercive. So therefore, we can prepare naturally for the initial data. So therefore, the initial value problem is well posed. It is okay. But now we would like to know that in the linear case, so Isobe-Kakinuma model is the higher order shallow water approximation. But it's not so trivial that the nonlinear term follow that precision, that higher order precision. We have to show that part. So in order to show that, we rewrite the equations in the non-dimensional form, introducing some non-dimensional parameter, and we would like to compare the solution of the full model and the Isobe-Kakinuma model. So let lambda is a typical wavelength and h be the mean dips. And we introduce a non-dimensional parameter delta, which is a ratio of the mean dips to the wavelength. So the shallow means this parameter delta is small. And we descale the horizontal spatial variable x by lambda and vertical spatial variable xn plus 1 by h and so on, as usual. Then we can rewrite the Isobe-Kakinuma model in the non-dimensional form like this, which includes the non-dimensional parameter delta here and here. This part represents some essential singularity of when delta goes to 0. And also here and here. And in this scaling, in this non-dimensionalization, this dips, local dips h is written by this. So the mean dips is rescaled by 1. And we impose initial condition as before, like this. And then the necessary condition for the existence of the solution have this form, which is almost the same. But we have some small parameter delta here and here and here. And as before, we need to relate the canonical variable with the variable of the Isobe-Kakinuma model. So this relation is given by this. Here, this is a canonical variable, and this is a variable of the Isobe-Kakinuma model in the non-dimensional form. Okay. Now, we want to compare the solutions of the full water wave problem with the solution of the Isobe-Kakinuma model. We need to rewrite the full water wave problem in the non-dimensional form. So this is a non-dimensional form of the Zaharov formulation, Zaharov-Craig-Slem formulation for the water wave problem. And we impose initial data like this. And concerning to the well-posedness of the solution of this full water wave problem with small parameter delta for some time interval independent of delta was already solved by, for example, myself, and Samaniego Lan also gave such a result. And also we gave some justification of the shallow water approximation in these papers. But anyway, we have some solution for some time interval independent of delta for the full model. Now, we consider the following two cases. The first case, we choose Pi equal to 2i in the case of the flat bottom. And in the second case, for the general bottom topography, we choose Pi is equal to I. And initial data for the canonical variable satisfy some regularity and the positivity of the bottom. Then finally, we show that result. So under previous assumption on the initial data and the bottom topography, the necessary condition and the relation between the canonical variable and the variable of Isobe-Kakinuma model determine uniquely the initial data for the Isobe-Kakinuma model. And let eta ww and phi ww be the solution of the initial value problem to the full waterway problem, and eta ik p0 blah 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 phi n be the solution to the initial value problem for the Isobe-Kakinuma model with this initial data. And we define the corresponding canonical variable phi ik by the relation 12. Then the error between these two solutions is given by this. This order was already appear in the previous theorem concerning to the phase speed. It is the same order. So in the case of the flat bottom, we have this order, and in the case of the general bottom topography, we have this order. So this is some sense the answer of the previous question of Professor Bonsk. So yeah, so this order is really high. As I said before, in the case of the shallow water equation, nonlinear shallow water equations, this error is of order delta square. And I did not write down the Green-Nagel equation, but this is known as a higher order shallow water approximate equations. This is very, very known in the coastal engineering. And in that case, the order is delta to the power 4. But here, even in capital N is equal to 1, we skip this order. It's extremely high. In some sense, I surprised. In the beginning of my research, I saw that this model is not so good model. So therefore, I tried to convince him the Green-Nagel equation is much better than his model. But finally, I was convinced that this model is good model.
So your initial data is
yes.
more regular than this function space H equals to the well-prepared initial data in the previous assumption?
Yeah.
In the same class?
Yeah, almost technically there is some small difference, but in some sense there is some small difference. So here the class of the initial data is constituting the eta hm and phi. We do not want to impose phi itself. The gradient of phi, it means the velocity. So it is more natural to impose the integrability. And this means that the phi is also hm. And in that case, the initial data for the Isobe-Kakinuma model satisfy this one. So this is almost the same. Maybe it's yes. And this one, here this part, we have some integrability. So therefore, because the equation is an elliptic equation, so therefore the regularity should be the...
For your main theorem, you had assumption of the initial data, right?
Aha. I do not write down the regularity of this part. Yeah, in general, if we work on the shallow water approximation, we lose many derivatives in order to get high delta. So therefore, we impose really high regularity of the initial data. So, but this is the essential feature in the shallow water approximation.
How about the existence time t, approximate time t? T is independent. Capital T is independent of everything else.
Independent of, for example, independent of delta, and
So this is like as long as you have a solution, right? For the
no. It's a small one.
It's small.
Yeah, but if initial data is small, it becomes long. So if we introduce a nonlinear parameter epsilon, then the time interval is of order 1 order epsilon as usual. So therefore, if initial data is small, so we can. But in general, we have, for example, in the shallow water equation, which is same as compressible Euler equation. So we have some singularity in finite time. So the long time existence is impossible. And I just present my result. I do not talk on any. I'd like to explain. There is another higher order shallow water approximate model. For example, Professor Matsuno, he is a Japanese physicist. He's a physicist. He is graduated from the Department of Physics in Kyoto University. And he derived extended Green-Nagel equation as a higher order shallow water approximation. And he called delta 2n model. So delta 2n model is an approximation of the full water wave equation with an error of this order. In our case, this is 4. Yeah, in his case, this is 2. And the linearized equation of his delta 4 model, which means the error of order delta to the power 6, where in our case, the delta n is equal to 1, is correspond to this one. But this is ill-posed. Unfortunately, this is ill-posed. So this is not so good model. And the linearized equation for his delta 6 model, this is the next order model, is well-posed in the linear case. For the nonlinear case, I don't know. Nobody know for the moment. But they contain 7th order derivative terms, so it's too high. So the coastal engineer do not accept such a higher order derivative to do the numerical computation. It's too much high. So compared to his model, the advantage of the Isobe-Kakinuma model is the initial value problem is ill-posed, always well-posed. And this is a higher order shallow water approximation with an error of this order, which is bigger, almost twice. And it does not contain any higher order derivative term. So the Isobe-Kakinuma model is a system, but the system of second order PDE. And the approximation hold even in the strongly nonlinear regime. We do not assume any weakly nonlinearity. For example, the KDB equation, the BBM equation, we need to impose the weak nonlinearity. But here we do not need to impose such a smallness condition. And for me, what is interesting is the following. In the case of the flat bottom, the solution of the full water wave problem in the non-dimensional form has this formula. Here we have delta, and we, in a sense, we approximated our velocity potential like this in the non-dimensional form. So the error of this approximation is of order delta to the power 2n plus 2. So we approximate the velocity potential in the Lagrangian with an error of order delta 2n plus 2. So therefore, it is natural to expect that the error of the real solution is this order. But in reality, this is for n plus 2. So thanks of we take some variation. So I cannot explain well. Maybe I do not understand so well for me, in some sense, in the calculation of the variation, some miracle appear, and it becomes double. For me, in some sense, surprised. And the structure of the Isobe-Kakinuma model is, in some sense, interesting. So we can, roughly speaking, we can write down the Isobe-Kakinuma model as this formula. Here, K is a Q-symmetric matrix, and A0 is a symmetric positive operator in L2. But this is the determinant of this Q matrix is 0. So in order to obtain the energy estimate, usually we take the scalar product with the equation with capital U itself. But in our case, in this case, we should take the inner product of the equation with the time derivative of U. Then this is Q-symmetric, so this term disappears. And we have the inner product of this part and the time derivative of U, from which we can easily obtain this energy inequality. Actually, this quantity corresponds to the physical energy. So therefore, it is what kind of positive equation for which whose solution satisfies this energy inequality, which is the following. So it is natural to derive the equation of this form, where A0 is the same as this one, and A1 is a Q-symmetric operator in L2. In such a case, the solution of this one easily satisfies. We can show that easily satisfy this energy inequality. So the point is we transform these equations into this standard form of the symmetric positive system, and then we can show the existence of the solution. Maybe I should stop here. Thank you very much for your kind attention.